The first two webinars on conventional sediment transport and the mudflow component are available to you now on the website under training and sediment transport, or whatever she categorized it as. So today we're doing in red here the mudflow sediment yield webinar, and then next week we'll be finishing up this series with the two-phase flow for mudflows and tailings dam breaches, and that will include just mudflows, two-phase flow in channels and together, not just for tailings dam breaches. So let's go ahead and get started here. And the other thing I'm going to do today is at the end, I'm going to discuss a little bit about hazard mapping for mudflows. So, okay, let's talk for a minute about physical factors that lead to the development of a mudflow in a hydrologic condition, meaning that it's generated from a rainstorm or as a flood event. And you know, in all of these cases, the objective is going to be, and this is a very interesting proposition for you, because I like doing this. It gives you the opportunity to match the potential sediment supply with what the model is predicting in terms of both the water volume and the sediment volume to get the total bulk volume of your mud or mudflow or mud flood. So, you know, the thing that you should do if you're going to design some mitigation, prepare some hazard mapping, or maybe replicate an event, is to go make sure that you understand what the watershed looks like under its existing conditions. And so that requires you not only to maybe sit in the office and look at aerial photographs or satellite imagery, but to get out into the basin and walk up and down it a little bit and understand what's going on, because what you want to see is how well developed the runoff will be. Is there a fairly extensive drainage? Is the channel development pretty complete? What is the sediment availability in the watershed? And we'll talk about this in some detail today. Is there anything that's stimulating the potential for a mudflow, including fires or logging or loss of vegetation in some way? How much debris is available? In some watersheds, you'll not only have boulders, but you might find refrigerators, you know, car bodies and so forth, which can contribute to frontal waves. And then finally, you know, how rough is the entire flow system in terms of channel roughness and overland flow roughness, and what kind of constrictions and storage might occur in the watershed. And again, very important, what we're going to try to do here today is to match the potential sediment supply in terms of its volume with what the model is going to be predicting. So let's start with the channel. If you're walking up the watershed, one of the things that I like to do is to try to envision what the channel might look like during the flood event itself, or mudflow event. And so I drew this diagram here. First of all, there's this curvaceous rectangle or square here. And let's say that this is the potential flow area that would evolve as the flow came down the channel. So that means that there's going to be some erosion, and typically if it's a mud flow, it tends to make this channel more U-shaped, a little bit like what I've drawn here. But what you should also understand is, where's the sediment supply coming from? Well, it may involve some scour through this material down to bedrock, and if there is some scour, in this case, you have these rather steep banks that exist in this triangular shaped channel, and this channel is going to become more trapezoidal shaped or U-shaped, and you'll see that if you walked back up into this watershed after the event occur, it might look something like these outer bands here. So walk the channel, estimate the depth of bedrock, take some pictures, get an idea of how many reaches you might have, where there is some storage of material, and I call it having the channel charged with sediment and boulders and maybe some debris, logs, and so forth. And try to get an idea as you walk up the channel, how much of the channel or how deep the channel might scour in order to reach bedrock. And you can make a pretty good guess at this. Sometimes I take a hiking pole or a rod and dig and try and spike down a little bit through the material, but that's kind of hard to do. So in evaluating the potential for a mud flow, please understand that in terms of a hydrologic basin, that is not a basin that's necessarily um, generating mud flows from landslides, but rather those watersheds and basins that where there's a intense rainfall that occurs. And so see if you can get an idea, and you can do this from both the alluvial fan as well as from the watershed, what the recharge period is after a mud flow event or flood event. And the reason for this is that it kind of defines what your return period is going to be for your mud flow event. Some watersheds, and it depends on the geology, of course, but some watersheds may only require a 10-year period in a more wet environment in order to significantly store and recharge the lower part of the basin, mostly the channel, with sediment. And then, this may involve 2 or 3 smaller events that might be on the order of the 2-year event, or maybe a 5-year event where the frontal wave brings some material down, maybe brings it down past the fan apex, past the mouth of the canyon, but yet leaves a lot of material up in the channel. Because typically a mud flow will occur in a basin with a return period of something on the order of 10 to 25 years. And you'll see a little later on why it's difficult for the 100-year event to actually generate a mud flow. So as you walk up in the alluvial fan and then up into the basin and you investigate this, see if you can define what the recent events have done in terms of how they performed or behaved, in terms of whether they were a mud flood or just a flooding event with more or less a very light sediment load, a conventional sediment transport load, whether they were a mud flow or mud flood. Now, if you have any issues with these definitions and you missed last week's presentation, I went over and showed some movies. So get the video from the last webinar if you want to have a refresher on mud flows and mud floods. But you should be able to glean some idea of how the flood event's going to behave from the fan deposits. And that includes whether you have bouldery type levees that confine the event and what kind of low bait deposits that you might have down on the lower part of the fan. Go up into the basin and see how much, again, loose boulders and debris there might be, because that's going to contribute to a frontal wave. Have an idea of the fan slope. Now, if the fan slope is fairly steep, generally that's an indication that you're going to have a mud flow event, or the mud flow is going to be defining the geomorphology of the alluvial fan. If it's more mild, it means that the flood event is getting carried down from the alluvial fan apex without depositing a lot of material. And so that tends to be more associated with a mud flood event. So look for different types of hummocky or berm type deposits, um, and then grab a sample. Find a spot where there's a deposit and you can take off the boulders and surface coarse material and dig down a little bit so that it's an undisturbed deposit, meaning that it wasn't washed in the recession during the recessional limb, and grab a small deposit, just a small quart Ziploc bag or so, back to the lab and sort it, do a sieve analysis, and see how much silts and clays you have in it. Because if you have sufficient silts and clays, and you must have some clay material to get a real good mud flow established, um, typically the range of the silts and clays, that is the percent finer than 0.0625 millimeters. Some people use 0.074, but 0.0625 millimeters and smaller, that fine material, the fine sediment, has to have a concentration by volume on the order of 5 to 10%. Now, you probably won't get much more than that. You might have 10, 12, 15%, but that's pretty uncommon unless the basin's very unique in its geology. Most of the mud flows in the western United States have silt and clay size fraction on the order of about 10 or 11%. So you can verify this with a laboratory analysis. And that doesn't mean that you have to do the viscometer analysis that we talked about last week. And I showed you where you could, gave you some clues as to where you could obtain a viscometer, though, if you wanted to get the laboratory and do the laboratory analysis for the viscosity and yield stress as a function of concentration. So we talked about that last week. So you're going to examine the watershed for existing conditions. But the idea is, looking at the existing conditions, try to project what the future might hold in terms of a flood event. Are you years away from having the channel charged with enough sediment to actually contribute and create a mud flow event? Or is it already charged? And when was the previous event? Typically, most people are going up into the watershed immediately after event to find out whether or not another event is going to occur in the near future. And typically when you do that, it's washed pretty clean, and you could say, well, I don't expect another event for, uh, several, unless you have several smaller events in the intermediate period. And what you should do in that case then is identify for the client or for the agency how long you expect it to occur before the next event might generate a mud flow event, and that they're going to get flooding on any future rainfall events, and that they should make periodic inspections, especially after a small, say a seasonal rainstorm or several small rainstorms in the watershed, and get up and take a look and see how much material is been stored in the channel. So, um, oops, sorry, I went a little too fast. I've been in a number of these basins throughout the western United States. This is a very clear mud flow basin. If you walk up this, it's a little difficult to walk up in this because it's so steep through here, but here's the generation part, the sediment generation part of the watershed here. Here's the transmission or transport part of the watershed, and then the depositional zone is on the alluvial fan. And if you look at this fan, you can see some young aspens growing on it, which means that it hasn't devastated this portion of the fan in some period of time, and maybe the flow has been coming down this side of the fan. You can also see that it's a fairly steep slope, which is an indication that it's a mud flow watershed. Um, there's a number of, if you walk down on here, you'd see a number of frontal wave low bait deposits or berms or terminal deposits. This particular brush in here is one. It grew up through the bouldery low bait um, berm deposit here because it wasn't being moved, so the vegetation, it was a fairly large event. There's quite a few exposed boulders on this alluvial fan. The deposits are very poorly sorted, and you can see that the existing path not only has some natural levees that have formed to confine it, but the path itself is rather tortuous. If this were a mud flow event, I'm sorry, a mud flood event, you would see this type of uh, uh, event come more straight down the watershed. A mud flow event will take a more tortuous path and deposit as it goes. So you can have a number of focuses in going both on a field visit to the alluvial fan and to the watershed itself. So look for some bouldery levees that help confine the flow. I showed you a movie last week that where the levee, you saw an event where the levees were actually being developed as it came off the out of the canyon mouth there down that constructed uh, channel lined with stone and so forth. And these bouldery levee deposits are really important because they force the flow with the material further downstream. So in terms of the supply, the typical sources are, there's 5 typical support sources of sediment for mudflow events. And we're not going to talk about volcanoes or tailings dam failures in this case. So there's landslides. Uh, there's a smaller form of landslides, just hill slope sloughing. Hill slope sloughing is the type of hill slope failure that might occur when you get channel bank failure. The bed scours, the bank starts failing into the channel, you undercut the toe of slope, and then the remaining hill slope sloughs down into the channel. So, and then there's overland sediment yield. So we'll talk about all of these a little bit. In most cases, for hydrologic type of basins that generate mud floods and mud flows, the primary sources are the channel bed scour and the bank failure. So what happens is that the channel bed gets lowered here, it undercuts the toe of bank, and the banks contribute sediment to the channel. And what limits this is when the channel scours down to bedrock, or there's bedrock exposure and on the banks themselves. So you want to identify the length of the channel that's actually might contribute to some amount of bed scour and some amount of bank failure. And in this case, I think we were estimating that there was about 1 meter of potential scour of debris off the channel bottom, but it would result in additional sediment loading of the banks here, and maybe even a small hill slope failure. But what identifies the limitation here is that there's quite a bit of vegetation that support where the root system is supporting the hill slope itself. So it might be limited in terms of the hill slope failure. Now, obviously, if the geology presents itself and you get landslides, and it may just be one landslide. Obviously, this is a case where there's a lot of landslides occurring, but one landslide by itself might contribute enough material to make a mud flow deposit or make a mud flow occur somewhere um, and reach the fan apex and pile onto the alluvial fan. The other primary source in a hydrologic basin generating mud flows is overland sediment yield. and the overland sediment yield can be greatly enhanced by fire in the basin. And I have some slides at the end of this PowerPoint presentation, about 10 of them, for post-fire analysis of sediment and potential sediment yield, but I'm not going to go through these today. I have a series of webinars that we could address at another time. So I'm not going to do that today. But let's talk for a moment about computing the overland sediment yield. Obviously, there's a lot of contributing factors. It's a function of, how much the particles exposed, the flow velocity and shear stress on the surface of the material, what the incipient motion and the incipient stress that is necessary to entrain the particle, and then all the particle material features, including density, how buoyant the particle is going to be in the flow because of the suspension of fines in the flow event and so forth. Now, a simple way to estimate overland sheet flow erosion, sediment erosion, is to use the revised universal soil loss equation or the modified soil loss equation. This is just an update to this equation here, to the original Muesli. We call it Muesli equation. And this will give you a yield in tons of sediment per acre per year. And you can convert this to like something like kilograms per square kilometer per year, or whatever you wanted, if you wanted to use metric. Some typical erosion rates, when you do this, you might see something on the order of 1 or 2 tons of sediment per acre per year. Pre-fire, post-fire, you can get up to 5 tons per acre. If you have a high intensity burn on a very steep slope, you can even get 10 times that. So I wanted to mention that the National Natural Resources Conservation Service, the NRCS, has a spatially based ArcView model that will help you to apply these equations to generate sediment yield. I don't know what the extent of that is, but I suspect that it's on the order of a large portion of the United States at this point. Now, just mention here that fire will enhance the sediment supply for a mudflow event by increasing the fine sediment concentration. This will change the size fraction distribution that might be in the bed, and this causes a decrease in the particle fall velocity and an increase in the buoyancy, so you can transport more larger boulders and so forth. It increases the fines when you load it, and some of this might be organic loading too, and the fine material, the ash and so forth, will increase the fluid matrix viscosity and the concurrent yield stress too. So if you have a fire, you might want to look, when you go up into the basin, try to, once a fire occurs, you need to be in that basin quite frequently, once a year if it's seasonal, or maybe a couple of times a year if you're on the West Coast and you get rainfall both in the wintertime and in the summertime. But the watershed recovery might be anywhere from 1 to 3 years before you start getting enough vegetation to support and limit the supply of sediment off of a previously burned basin. And this, of course, is dependent upon where it occurs. Now, again, I mentioned that I have some extra post-fire sediment yield slides at the end of this presentation for you. So to simulate a mud flow event, or to combine the concept of how much can I have a mud flow event with an analysis of the supply, the first thing that I would do is estimate the sediment supply. Then you want to develop an inflow hydrograph rainfall runoff event at the fan apex or the basin mouth. So you can do two of these either. Well, you do the first through a little bit of hand calculation, and then going up into the basin and doing some field reconnaissance and looking at some aerial photographs. You do the second one. You can do the second one with a any kind of rainfall runoff model, or you can use Flow 2D in the watershed, and you can do the Flow 2D in the watershed and on the alluvial fan all in one model if you wanted to. Typically, I do the watershed separately just so that I have an inflow hydrograph that I can play with. It could still be in the same model, but then I put in an inflow hydrograph, somewhere just above the fan apex. And so I have an inflow hydrograph that I can bulk for sediment to analyze and match with the supply. So I'm going to assign a sediment concentration to the inflow hydrograph pairs. This is more or less a guess. We're going to look at this in detail here in a second. Then I'd run the model. I'd review summary.out. I'll show you how to compute the average sediment concentration from the information in the sediment.out file, summary.out file, and then compare these with the sediment volume and compare the computed sediment volume with the estimated supply that you made. Now, alternatively, you could try to generate sediment using a sediment transport equation to generate the sediment supply, and/or you could try to replicate a recent event with the estimated deposits that you may survey on an alluvial fan. But if you had a recent event and you have mud flow or even mud flood events, then you'd want to probably still estimate the sediment supply and then try to see if it matches more or less with what your deposits are. What you have to remember, though, is that everything that's run off the fan and down into a river channel somewhere, or just out onto a peneplain or wherever the flood eventually has dissipated to, you're going to have to include in that runoff amount a sediment concentration by volume, so that you account for that amount of material that's not in the deposits on the alluvial fan. So I'm going to try to give you an idea how to do this. You're sort of on your own here, but I'll give you my best approach to doing this, and it's kind of fun. It gives you it allows you to use your engineering judgment on how to approach this. And what we'll do is we'll talk about this in terms of a watershed type of event. Now, so I'm not going to talk about landslides or hill slope failure, but if you see in the aerial photographs some evidence of historical sediment landslides or hill slope failures, then I would maybe include one of those and estimate how big that slide was. That slide, however, may be an anomaly, and the watershed itself is just delivering sediment with the hydrology of the storm event. So what we're going to talk about here is the other three, with the channel bank failure and the channel bed scour being the primary sources of sediment, and then the overland sediment yield being more secondary in most cases, unless you have a fire. So don't panic here. I'm doing this for you because it's this back of the napkin approach, but this person who did this did a pretty good job with it, just by estimating some sediment yield in a fairly straightforward manner. And so I'm not asking you to try to read this or anything. It's just to give you an example of how you do this on the back of a napkin type of approach. So there's three sources of sediment supply here. bed scour, bank failure, and overland sediment yield. Now in the first one, lost my mouse here, hold on. Well, in the first one, in the bed scour, um, what we're going to look at is how well defined the channel is. So you want to measure an approximate length of the channel, what its average width is, and based on your field inspection, how much of the sediment bed scour you would get in this estimate. And so it would be a certain amount of volume associated with just the bed itself. Now, if you have different segments of the channel delivering different amounts of sediment, then just divide it up a little bit. Then in terms of the bank failure, um, what you'd want to do here is estimate, from your bank uh, scour on maybe one side. It may not have, if this occurred in the wintertime or something, if you had a mud flow in the wintertime, as I investigated one in Idaho, um, one side of the basin, one side of the watershed was yielding sediment. The other side was not because it was still frozen. One had a south facing slope, the other had a north facing slope. So you want to make sure that you go up into the basin and identify different reaches that could deliver different sediment. But you can see that this person, estimated um, a top of bank, a rough approximate thickness of the the banks that might come into the channel, how long it was, and again, just trying to estimate the volume from this. And then finally, the overland sediment yield using the universal soil loss equation. This is where it has this um, runoff factor from the revised universal soil loss equation, Roosli as opposed to Muesli. Um, and what I would do in this case is, you'll have to look this up on your own because these factors some of the factors are sensitive, some of them are not, and it's not worth my effort here to go into that deep of detail for it. But you can apply this equation and give yourself an estimate of sediment yield. So then what you want to do is add all these up. And in this particular case, you might estimate that the supply is around 5 acre-feet or so. Then develop your hydrology and compare with the water volume. I want to make sure okay, never mind. I think my mouse has died on me. Anyway, down in the lower right-hand corner, we're comparing this with the water volume. And then if you add the sediment volume and the water volume together, you have the total volume, and you can estimate an average sediment concentration from the supply if you wanted to. What I have to remind you to do is that when you do an estimate of the bed scour, the bank failure, and the overland sediment yield, is to account for the porosity if you're taking this everything as a depth of sediment, because what you're computing in the model is a solid volume of sediment to compare with the volume of water in the model. So you have to convert one or the other. And in this case, if you want to compare directly the sediment supply with the sediment volume predicted in the model, you would multiply the 5 acre-feet by 1 minus the porosity, say 0.04, so it'd be about 0.6, and that would give you how much solid volume of sediment that you would have to compare with what the model predicted. So what you're going to do now is you've got this sediment supply, and I'm going to show you in a moment an inflow hydrograph and how we can bulk that inflow hydrograph for the sediment volume. But what I wanted you to see here first is that the sediment volume by the two blue arrows here is the difference between the bulked with sediment bulked volume minus the water volume. So it's roughly 36 or 37 acre feet minus 22 or 23 acre feet of water. And we wind up with about 14 acre feet of sediment, 22 acre feet of water. And if you divide that sediment volume by the total volume, right? We talked about this last time to get the concentration by volume. That is, we divide the 14 acre feet by the 36.73 acre feet of bulk volume or total volume. That is sediment plus water. And it results in a concentration by volume of around 38% for this particular watershed. Now, the watershed that I was showing you in the previous slide is not the one that I'm talking about here that had around 5 acre feet of sediment. But in this case, the sediment volume or the sediment concentration by volume is on the order of 38%, and you need about 30%, and this could range from 25 to 35%. You need an average concentration by volume on the order of 30% in order to generate the mud flow. Now, why would I say that? Because if you're going to have a flood event and the initial frontal wave comes down pretty quick, and maybe the peak discharge catches up with the frontal wave, and the mud flow is the frontal wave plus eventually the peak catches up with it. So on the fan, the peak and the frontal wave are about the same. Then you have this recessional limb, which is much more dilute, and it's running over. You might have 20% on the initial prior to the frontal wave. You might have 20% concentration by volume on the recessional limb of the hydrograph, but you may have 50% on the rising limb of the hydrograph before the peak arrives. Once the peak arrives, you're starting to dilute the concentration by volume, and you're dropping from 40, 45, maybe 50 to 55% concentration by volume as the peak mud flow concentration by volume. You're dropping that to maybe 40% or something when the peak flood discharge passes by the fan apex. And so that's why you need to have an average of around 30% throughout your entire event in order to have a mud flow. Now, that doesn't mean that if your concentration by volume is 20%, you're not going to have a wave of mud flow, but it's going to be short-lived. It's going to be a frontal wave. It's not going to be the entire major portion of the event. It's going to be a mud flow. It's going to be mostly a mud flood. On the other hand, if you had a landslide initiated event, you could have a fairly uniform concentration by volume, something on the order of 45 to 55% concentration by volume. And we talked about this in detail in terms of what kind of behavior you should expect out of different concentration by volumes in the previous webinar. So in order to create a mud flow simulation here with Flow2D, you need to have an inflow hydrograph. So this inflow hydrograph now is going to be in the inflow.data file, and it's going to consist of 3 columns for mud flow event. Now this is making the assumption that you develop the water flood. Maybe this is the 10-year event, maybe it's a 25-year event, could even be the 100-year event if you wanted to look at it, although I don't think you're going to have a mud flow for the 100-year event. And you're going to see that you've got the first 2 columns developed from your hydrology of your basin. And you can see that the peak in this case occurs at about hour 1.33 at 730 CFS as the peak discharge. And you can see that what I've done here is I'm assigning the 3rd column as roughly 20% with the first initial runoff in the lower part of the watershed. And then as it approaches the peak on the rising limb, I bulked the next hydrograph pair, 403 CFS by 45, maybe 50% concentration by volume. And then after that, I decrease it, even though you might have a few waves after that that bulk up a little bit as you get this kind of resurgence and surging of the mud flow coming down. I basically decrease the the concentration by volume on the rest of the hydrograph back down to about 20% concentration by volume. So even when the event is back down to 10 CFS or so at the end of the hydrograph, it's still flowing something on the order of 20% concentration by volume. Now there's another way to do this, and that is add the actual volume at this particular grid element, which may be located just above the fan apex by several grid elements, and I'm loading it with the actual volume of material, 100 cubic feet, 500 cubic feet, or cubic meters, if whatever you have there. And I just bulk it up however you want it. And this is just to exemplify how you might bulk it. You could do it fairly instantaneously with a landslide event too. So there's nothing unique about these numbers. I just made them up and put them in there so you could see that there was some variation in the numbers. I might arrange it so it went from 100 to 1,000 and then down or something like that. After, with concurrent time, successive time intervals, input pairs. But the reason I'm telling you this is because either the concentration by volume or the volume itself being put in is more or less a guess until you get to this point and you get output and you start comparing these two and you make the average concentration by volume calculation. So if you're down at 20% and you're expecting a mud flow, you want to go back and increase your concentration by volume. So what I would do is go from 45 to maybe 50, 52% concentration by volume, and then further reduce that through the peak and so forth until I got the concentration by volumes a little higher, maybe distribute it all the way down. But then what gives this some justification is that you have this sediment now that you're predicting by the model, and you can compare it with your supply estimate that you've made from your basin. And I suggested that you be conservative in estimating that supply, maybe, come up with a supply, multiply it by 1.2 or 1.5 and see where you fall and compare it with the 10 to 25 year event and see if it would generate concentration by volume in the 30 to 35% concentration by volume range. And if you can do that, then you've got a mud flow event. If you can't do that, then you've got too much water in your basin for the 25-year event to do it. So now when you want to do your project, whether that's a mitigation project, a replication project, or a hazard project, you're going to come up with some different scenarios. And maybe you have developed a hydrograph for the 2-year, 5-year, 10-year, 25-year, and so forth events. And also maybe you have a historical event that occurred last year. And so you might have some estimates of the hydrology. You might have the rainfall amount. You may have, it's unlikely that you have a gauging station or anything like that, but it may have filled a debris basin. So that might be a good opportunity to, especially if it was a small a small event and it didn't fill the entire basin up, you would have both the water and the sediment volume in the basin. So you want to develop the hydrology, however you wanted to do it, either as a design event or a historical event, and then do the water flooding for these different events, and then maybe do a low sediment concentration where you bulk the flows by 20% concentration by volume. Now, if you do this, you can just set the X concentration factor equal to 0.2 in your control.data file. This would run the model without doing the mud flow, mud flood, viscosity, yield stress, etc. analysis. Then finally, the third, so that's water flooding, a low concentration where you're just trying to bulk the flow, the actual water flooding, so that you're getting a more representative flood event instead of just clear water. And then get on into the mud flow analysis and maybe do some mud flows with the CV variable, or if you have a pretty good handle on the sediment supply at a location, you can enter the volume and then do the mud flow for the 10 to 25 year events, and maybe just a bulked flow for the 100-year event. So in small watersheds, particularly less than 5 square miles or so, infrequent flood events such as those on the order of the 100-year event generally do not create very viscous cement-like mud flows. Why? And the answer to that is there's too much water in the 100-year event for the available sediment supply in your basin. And this may be true even for burned watershed. So what you want to do is to estimate the sediment supply, get into that basin and do a crude estimate, and then play with the numbers a little bit. You know, suppose it's 1.5 times that. If it's 1.5 times that, and you look at the volume in your 100-year event, and you cannot get that concentration by volume, average concentration by volume, up around 25 to 35%, you're not going to have a mud flood or mud flow. You're just going to have a mud flood. It's just going to be a flood event. So let me show you now a movie where we can look at the sediment supply delivery and then the sediment bulking as it moves down the channel and onto the towards the fan apex. So I'm going to show you the evolution of the event in the basin. I may have trouble doing this because my mouse has stopped working. I can't push the button. So I'm not sure what I can do here. Let me see if I can just change the battery real quick. Bear with me a second, because I bet that's the problem. Bear with me, it just take a second. I suspect that wasn't the problem. Yes, it was the problem. I wasn't a member of the international mouse battery changing team, so it took me a while to do that. In deference to the Olympics that are going on, I don't think they have a mouse battery changing event. Okay, so let's see if we can watch this film now. I'll blow it up for you. Okay, so here we have this, you can clearly see it's water, and then here's this watershed which is delivering a lot of sediment, and it's changing the color from here down. But right now this is just bulked by maybe 20–25%. But here comes this load of sediment. It's raining, obviously. And here comes this load of sediment from this watershed delivering the sediment. So this would be a clear point in which you would add the sediment. Now watch what happens to this. As the sediment comes down, it starts eroding more sediment. You get a bouldery frontal wave because the boulders are riding in the core and moving to the front. And pretty soon, the frontal wave is holding everything back a little bit, so the peak water discharge is catching up with it. That was a lot to say. And you can see the bank failure in here. So it took quite a bit. There was a fairly small amount of sediment that was coming off this basin, but most of the sediment was loading the channel from the bed and bank failure downstream of this location. Let's watch that again because it's fairly instructive. You can see that you're somewhere on the order of 20 or 30% concentration by volume based on the sediment loading from this. You can see some of the sediment coming off this fairly erosive structure here. This is more bank failure and hill slope sloughing coming down, but now it's moving into the channel. Okay, and there's some sediment here, but watch where it mobilizes all this sediment in this next reach. And you can see that it greatly increases this amount of sediment from the bottom of that basin, bottom of that channel. Okay, so let me stop this. And move on to the next slide. Oops. Okay. So now this is the same watershed, only it's down around the corner. And here comes that frontal wave that we were just watching. So now the frontal wave and the peak discharge, they're essentially caught up with each other. And you're watching this occurring as a mud flood, according to the definitions that I gave you last week. This is behavior, very fluid behavior. It's mostly a mud flood event, but it's got a significant frontal wave, and the frontal wave is withholding the timing of the event a little bit. Frontal wave would flow slower than if this were just singularly water by itself. So that was instructive as a supply, a source of sediment. Okay. So let's talk a little bit about hazard mapping now, to kind of pull this all together here. Hazard maps should be a series of maps for your client that include flood inundation, hydraulic intensity, maybe meaning that predicted maximum flow and velocity depths for existing or future conditions, and then some hazard mapping analysis so that you can identify whether a certain portion of the alluvial fan or floodplain is going to be high, moderate, or low hazard. Now let me start this discussion by just suggesting to you that hazard is not risk. Risk and hazard are two different um, uh, beasts. The hazard is an event that poses a significant danger. Vulnerability is your potential to be exposed to that specific hazard. It's how susceptible a building or a person is to getting flooded. Risk is the probability of suffering the loss associated with the flooding. And so you need a dollar or a loss of life. You need some way of measuring the loss. So the hazard is, as defined by the UN as ISDR in 2004, a potentially damaging physical event that may cause the loss of life, injury, property damage, social and economic disruption or environmental degradation. The flood hazard is defined as the exposure to flooding. Now, risk is the probability that there's going to be some consequences with this, some expected losses, deaths, injuries, property damage, etc., resulting from the interactions between, the hazard itself, whether it's natural or human caused, and how vulnerable the conditions are, how susceptible you are to these hazards. So when people are discussing risk, they talk about, people are going to be in the risk, they're at risk because of the flood event. What they typically mean is hazard. They're in the hazard zone. where risk is the intersection of, if you're looking at it in a mathematical sense, the subset, uh, uh, the subsets are hazard and vulnerability. Risk is the intersection of hazard plus vulnerability for a specific event. Now, if all of this is a little confusing for you, I present to you this very demonstrative example to define the difference between hazard and risk. Here's the Sacramento River in Sacramento, California. And you can see that there's one portion of the floodplain that's well developed and the other portion is just farmland. If you were to have a major flood event and resulting in, say, 1 meter of flooding across most of this floodplain, overtop the levees, um, and the flood depth on both sides of the river was roughly 1 meter or 3 feet or something, then you would have essentially equal hazard on each side of the river. But while you have a similar hazard, the risk associated with the loss on both sides of the river are extremely different. This has much higher risk than just flooding the farm fields. So this is an example of the corresponding definitions between risk and hazard. So I promote hazard mapping because they're easier for the public to assimilate than FEMA maps. In the United States, we have these FEMA DFIRM maps, which are, just for the insurance companies. They're absolutely useless, and most of them have been done with HECRAS 1D models, and so they're completely false. Even those that are being done with the FEMA HECRAS 2D models are pretty poor because they don't have any real urban features in the HECRAS model, like storm drains and stuff like that. So the FEMA maps are really kind of, basically, to the benefit of the insurance companies, which is defining our flood hazard in the United States. It's a joke. What hazard maps should be doing is making it easier for the public to assimilate DFIRM maps or the hazard. And this is what's occurring at this point in the last 5 years. I don't want to toot my horn too much here, but I started generating these maps back around 2000, and you'll see them in a second. And I have been promoting the use of flood hazard maps for the last 22 years. It's only been recently in the last 10 years that we've gone to HAZUS mapping and other types of hazard zone mapping. And it just shows you how long it takes for government to respond to obvious things that benefit people. So in the case of hazard maps, we have 3 flood hazard zones. These are a combined function of the flood hazard hydraulic intensity, or the severity of the event, and the frequency of the event, although you can do it for just one event. The hydraulic intensity is some function of the flow depth and velocity, and the event frequency, if you want to use it, you need 3 different simulations for 3 different return period events. So this depicts these. If you have an alluvial fan, you might have flow depth, velocity, this is hydraulic intensity, and then you generate the hazard map from this plus the different return periods, or for a given event. This would be a hazard either for, like, say, the 20, 100, and 250-year event, or the 5, 10, and 50-year event, or something. You could generate this as a function of frequency, or generate this hazard map for just a given event, say the 100-year event or whatever your design event might be, and associate it in that manner. So what these hazard maps do is they are combining and interpolating between high hazard events and frequency. When you have a very high hazard 500-year event, it occurs with a fairly low frequency. So it may pose a less hazardous scenario than having a high hazard from or a lower intensity hazard based on the 10-year event, but a more frequent occurrence of the hazard. Now, different hazard intensity maps can be generated. It can be just solely a function of flow depth, which is what we do with the FEMA maps, um, or like in Austria and Switzerland and other places in Europe, you can do depth and v squared over 2g, or depth and velocity times depth. And then this would be an interpolated function of these two. So in doing this, we've incorporated into the model these hazard maps for people, for houses, and so forth. And these were generated by the US Bureau of Reclamation in the United States um, as a hazard map, which is velocity and flood depth together, where you have low, medium, and high danger zones. And likewise, you can do this for houses. And so this has all been built into the model. So you can create these maps, high hazard, medium hazard, and low hazard, and give it some description. This is just for as an example, which you would present to your client. People are endangered both inside and outside structures. For a high hazard, the buildings can be destroyed. People are endangered only outside of the buildings, and buildings might suffer or be possibly destructed um, based on its construction, meaning that is it a block building or just a wood frame building? Is it on a basement? Does it have a basement, and so forth? In yellow hazard, it's just inundation um, um, hazard. So you can define these in the mapping tool we have, which is Mapper, and you can define these limits if you want. We make some suggestions for you, and you would do like the maximum depth, or the product of the maximum depth times the velocity, or either one. You can do it that depth and v squared um, over 2g, or v squared times h over 2g. So the typical hazard map looks like this. When you do it either by interpolation or for a single event, either you interpolate the frequency, 3 different events, or you do it for a single event. And what this gives you is a high hazard area on alluvial fan, a moderate hazard, and a low hazard. Now, this doesn't mean that you're telling people that they should go in and develop on these low hazard areas. But what it does tell you, if that people are living in these red zones, you should make an attempt to get them the hell out of there. There should either be opportunities for evacuation or just remove the houses altogether. And that's what these hazard maps do for you. What they don't do is tell you that, well, we're going to have 1 foot of flooding if your base floor elevation is 1 foot above the flood zone. You'll be safe, even though you're in the red area, which is baloney. I mean, you wipe out the house in terms of a mud and debris flow event here. So if you take these to a public meeting and show them to the public for discussion, they'll understand this. They'll be it's pretty clear. There there will eliminate some of the confusion that comes from DFIRM maps. And you can do this with fairly detailed modeling with Flow2D. You can do it for water flooding or for the mud flow. The water flooding, if you show these events for a given event and then you show them the hazard maps associated with these types of events, and you can have different criteria for the mud flow. You can have different criteria for the intensities for the mud and debris flow event versus water flooding events. So if you show them the inundation mapping, as well as, see, and this is all mostly shallow flooding in here, whereas the mud flow comes in and deposits deeper depths coming out of the alluvial fan, some deeper depths in here, and the flow's not going very far because the flow ceases as a mud flow event. But here the water continues on down through the through the urban area. Now, this enables you to, once you have these kind of hazards defined, you can help to manage your hazard or your risk and reduce the amount of damage, doing a number of mitigation measures and see how it might respond. And this is just a simple case. This is in California. All these watersheds burn periodically. There's even been some recent burning near these watersheds here. So we're looking at a 10-year event here. And this is with no storm drains. And so if you look at the area of inundation on this map, you can see it with the storm drains. And then if you go forward, you can see that the storm drains do have an impact if you can appropriately capture the flood event. So let me go back and forth here for you. And you can see the impact of the flood event and the hazard, managing the hazard risk. So these types of hazard maps, you can identify mitigation measures, reduce the hazard. This is just an inundation map, but I think you get the idea. So again, I'm at the point where I can stop the presentation now and stop the recording. I'm trying to stop the recording. It's not letting me stop the recording. I don't know what to do about that. Well, okay. Well, if it doesn't stop, it doesn't stop, I guess. I would like to show you, in addition, wonder why it didn't do that. Anyway, I hope that everybody got full access to the webinar. At any rate, I see that there's a number of people in this and that we have roughly the same number of people when I started, so I must be doing okay. But here's these post-fire sediment yield slides here, burn severity and several others. So next week, you'll have access to this PowerPoint presentation and the webinar. And let me see if there's some questions here. And there are some questions. Henry says, is muesli for sediment yield per storm? That's a good question, Henry. I'm not sure. Yes, I think so. I can't. Is it? No, it's not per storm, it's per year. So it's the average sediment yield per year. So in your storm analysis, if you have a 10-year, a 5, 10-year, 25-year, 50-year, 100-year, and so forth, what you need to do is do the combined analysis of those to get the mean annual volume for the sediment, for the water yield. And that way, that would enable you to have a average sediment yield per year and an average water yield per year. And then you can compare them in that way. Okay, could you please tell me if flow 2D model takes into account erosion of the channel and the increment of material? Yeah, well, yes, that's what we talked about. We talked about the bed material loading and the bank loading in terms of how much scour you would expect in terms of the supply. Now, if you want to compute a comparable erosion of the channel, you would have to use one of the sediment transport equations, and that gets into the concept of two-phase flow, which we're going to cover next time. So in terms of predicting the scour of the channel along with a mudflow event, we'll cover that next week. It's a little bit complicated. In general, for the mudflow portion of the model. The model will predict flow cessation and flow remobilization. For the sediment transport portion of the model, you'll predict scour and erosion. What are there additional considerations to use with modeling lahars, which are volcanic type of mudflows? The answer to that is, I would say, see if you can do some laboratory analysis to get the viscosity and yield stress. Now, that's a little complicated, but the the viscometers that are available will allow you to do an analysis like on asphalt. Those commercial viscometers that I talked about last time from um, Brookfield and Amitech, they will actually allow you to do an analysis of uh, asphalt. So that might mean warming them a little bit. I don't know if you want to do them, fully uh, lahar temperature being, several thousand degrees or something, but you might be able to warm them up and see how the material would use. So for lahars, the best thing you could do is to have um, the viscosity and yield stress relationships as they might vary from the mud flow relationships. On the other hand, however, if you don't have the ability to do a viscometer laboratory analysis of the lahar, just use the most viscous of the sediment uh, uh, mud flow deposits that I showed you last week. And typically that's Glenwood number 4, but you can do your own analysis of the samples. Are we able to change the mapping limits in the QGIS plugin as in the mapper? No, it's not in Simone. It's not in the QGIS, it's just in the mapper, and you can change them in the mapper, but you can't change them in QGIS. You have to call the mapper from the QGIS. How should we choose if the shape, CV, if the shape of the hydrograph and maximum discharge varies a lot in the range of CV equal to 20 to 35%? It does, and it's going to. And the only thing that I would do is to play with it and try a number of different scenarios. You will see the behavior change if you rebulk it and you get some incidental. You may even see the model generate some surging in the recessional limb. And if it does, that's a clear indication that that there should be maybe a little bit more variability in the concentration by volume in the inflow hydrograph. But the first thing you want to do is make the average concentration by volume match that of a mudflow event, and to see if that mudflow event could occur in your basin by having the sediment supply roughly match the predicted volume in the mudflow event. And I think that's the last of our questions today. Okay, so next week we're going to be doing two-phase flow modeling, and let me just see, I saw this shift a little bit. Doesn't look like we got any more though. Oh yes, we got one here. Okay, got a couple more. The unit in Roosley is tons per year. It's tons per acre per year, or tons per square mile per year. How should we convert this in order to add the estimate volume from the bank failure, which is in acre feet? Again, that's an average per year. So you would take that in terms of like an annual event, or from a 5-year event. You would want to do it for a given return period event and then get it in just tons per acre. But you can reverse that and do the water volume for the 5, 10, 50, 100 year event. And there's an easy way to do that. It's like point .02 times the volume of water in the 100-year plus the 50-year, plus the volume 0.04 times the volume of the 50 plus the 25 plus 0.5 and so forth, and you get it. There's an equation that does that. And when you use that equation, then you get the average water yield per year. Then you could do the water yield and the um, um, sediment yield in terms of an annual basis. But otherwise, you just have to consider that the volume of the Roosley is being analyzed for a given return period event. Can the discharge of the frontal wave be twice as large as the discharge of the rest of the hydrograph? Yes. What happens is that, as you saw in that first video that I showed you, is that the sediment loading is coming down on the rising limb. That frontal wave is flowing slower than the peak. By the time it reaches the fan apex, typically by the time it reaches the fan apex, the peak discharge catches up with the frontal wave. And then over the alluvial fan, the frontal wave can be more than twice as large as the discharge on the rest of the recessional limb of the hydrograph, because the frontal wave became the peak flow. It's a very short, intense event, feature of the mudflow event itself. Okay. All right. So that's the last question for today. So the questions may be included because I was unable to stop the recording in this particular presentation. So that's it. And wrap this up. We'll talk again next week when we present the fourth of the 4-part series on two-phase flow. Thank you very much for attending.